Hello everyone, welcome back to PMAC1140. I have to say that in this video, the concept we cover in this video might be considered as one of the hardest one in pre-calculus, and it's of course it's related to the previous one. In the previous video, we talk about factor theorem and remainder theorem, when we can determine with a number 0 of the polynomial by using the synthetic division, and if the remainder equal to 0, then that number, the number we do division by, will be the 0 of the polynomial, and that's why the x minus that number will be considered as the factor of the polynomial. The thing is that how do I know the number of 0 we have in a polynomial? So in this video, I will be talking about a very important, not just one theorem, but like several important theorem. It tell you exactly how many rational 0 polynomial might have, and how many 0 in the polynomials it will have. It depends on the n exponent, the highest exponent in the polynomial. So that theorem we call the fundamental theorem of algebra, and it was invented by the Gauss. Okay, so let's go through that one by one in this video. So I think will be the pretty long one. Okay, so be patient with me. Okay, so let's put the topic for today. So the topic for today will be, I think I'm going to use this one. I'm going to put rational 0 theorem. Rational. Okay, 0 theorem. Okay, this is tell you the number of possible rational 0 in polynomial. Then we talk about the fundamental theorem of algebra. Fundamental theorem of algebra. Okay. In the previous video, we also talked about, I mentioned a complex factor. So actually, those concepts come from the theorem by a theorem called the conjugate 0 theorem. The conjugate one. Just want to make sure I got the name correctly. The conjugate 0 theorem. Okay, 0 theorem. Okay, so it means that it means what? It means that 0 can be a complex number, could be rational number, could be whole number, could be the number could be the 0 could be positive or negative, and that's why we have to consider another theorem. We call that it's not a theorem, it's just the rule, and this rule created by Descartes. Okay, so this we call that rule Descartes rule sign. Okay, Descartes rule sign. Okay, rule sign. Okay, Descartes rule sign. Let's see. And at the end, we talk about the boundedness theorem. Boundedness theorem. Boundedness theorem. Okay, the boundedness theorem is also important because it gives you the the furthest frontier and the lowest frontier. I can say that the lowest boundary that contain, the interval that contain the zero, the rational zero, on the number line. That's what I mean. So all the rational zero must be in that interval. That's what the boundedness theorem for. Okay. So let's go one by one. Okay, let's go one by one. So the first one I will be talking about will be the rational zero theorem. Okay, so this is all the topic we had to cover in this video. Actually, in the last video, I already give you a bunch of problem, different example, too many example, right? It's good for you because for you to practice. Now, on the first part, let's talk about rational zero theorem. Okay. So the rational zero theorem will tell you the possible rational zero in the polynomial. The possible, the number of possible rational zero. Rational zero. The number of possible rational zero. It means what in this estimation, one of the number is not a zero, but we just estimate the number of the zero. Some of them it's not a zero, some of them yes. So that's why I say that it's just a possibility. The number of rational zero. And we know that the polynomial function is written as this: f of x equal to a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus the blah 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 blah. And at the end we have what? We have a naught. So in order to find the number of possible rational zero, we set up the ratio, and set a ratio between the factor of a sub 0, and factor of a sub n. So we're gonna set the ratio between p and p over q, and p is the factor, all factor of a sub 0, and q is on the factor of the leading coefficient a sub n. So we're gonna set up the ratio, then we'll give you all the possible rational zero. For example, I have something like this. Example number 1. What if I have polynomial p of x, and I have 2x to the third. Make sure you put everything in order, plus x squared, because it must be in order to determine the last digit, the a sub 0, plus 6. So this one I give you this in order. So now, in order to find all the possible rational zero, just possible, just not all of them is zero, just possible. Some of them will be zero, some of them will not. We're gonna find a factor. A factor of 6 will be plus minus 1, plus minus 2, plus minus 3, plus minus 6, and a factor of 2 will be plus minus 1, plus minus 2. And now we're going to set up the ratio. Alright, set up the ratio between this and this. So I can say the number of possible zero will be what? This over this, plus minus 1, this over this, plus minus 1 over 2, plus minus 2, 2 over 2 give you 1, carry the same, plus minus 3, plus minus 3/2. Okay, and 6/2. 6/2 is just plus minus 3. So how many possible one? Totally 12, right? Totally 12. Oh, and plus minus 6. Yes, totally 12. So we have 12 possible zero rational. Okay, just rational. I'm not talking about a complex right now. But in this one, which one? In all the zero here, which one is the real one? Which one is the zero, the true one? What I mean is that what number over here when you do synthetic division, the remainder is 0. Okay, we don't know. We gotta check, right? And of course, you gotta go ahead and do synthetic division for all. But we don't have time, right? How are we gonna do synthetic division for all? There's no way. It's gonna take a lot of time. So the best way, I'm gonna show you that we just go ahead and plug them in. For example, we put p of 1 into the function. We see that to 1 to the third. So 1 squared. I take times 1 plus 6. And we see that it will turn out to be 0 or not. Alright, just do a quick calculation here. Nope. This is give you -4. So of course 1 is not the 0. How about p of 2? Put it in. 2 squared. And 13 times 2 plus 6. Alright, go ahead and calculate them out. 20, 60, 16, 20. 20 minus 13. 20 minus 26. We need -6. -6. Here you go. This is 0. So it means what? It means 2. It means 2 is a true 0. Okay, 2 is a true 0. Alright, this is positive 2. And we gotta do all of them. Of course, we're not gonna take all of the time to do all of them, right? We can do another way. Between 2 is the 0, so we gotta go ahead and do synthetic division. So we do have synthetic division. We see that okay. We have 2 here, 1 here, -13 here, 6 here. The reason we do synthetic division is because we're going to get the polynomial, the rest of the polynomial. So this is, you drop it down. Alright. So 2 times 2 is 4. 5. -3. 6. See that? It gives you 0. So the polynomial we have left will be because it's the third degree, so it will be 2x squared plus 5x minus 3. Okay, and we gotta keep going. We gotta keep going. We gotta factor this. All right, we gotta plug it in and see which one. So let's say that this is p prime. Okay, the p star. I think I'm gonna put p star. Okay, and we can see which value over here when you plug it in give you 0. Or you can go ahead and factor this, because this is trinomial, and we can go ahead and factor it, and we see that the factor of this will be 2x minus 1, x plus 3, and now we have polynomial px can be factored as x minus 2. Excuse me. 2x minus 1 and x plus 3. And now we factor this polynomial completely. Now, okay, so I mean, a rational zero theorem, it help you, you know, it kind of give you the boundary. I mean you don't, because the two, how many number you have on the number, like too many, right? And how many zero we might have, we don't know, right? So the rational zero theorem can help you kind of perimeterize the zero, then see which number is the true zero of the polynomial. Okay. Well, I can do another one. How about this one? 2. going to have p of x equal to 4 minus 5 x to the third minus 5x squared plus 23x plus 10. Alright. And we try to factor on this. And let's say we try to find all the factor of 10. 1, right? So it will be plus minus 1, plus minus 2, plus minus 5, and plus minus 10. At the bottom we have only plus minus 1. So the total we have will be 8. We have 8 possible zero rational, not include the complex. Okay. And now we gotta go ahead and check. We do syntactic division. All you do, you just go ahead and plug them in. I think I'm gonna do syntactic division. How about we go do find? I'm just pick random positive find and do syntactic division. Okay, and up and down 0, -5, -25, -2, -10, and you see that the remainder is 0. So the polynomial we have left will be equal to x to the 4. So the polynomial we have left, I'm gonna call the p star, will be x to the third, x squared we don't have it, minus 5x minus 2. Okay, and now we gotta keep going. We gotta keep going to see which one can go into, what number over here can go into this and give you the remainder 0. So let's keep checking. I'm going to check 2. How about I check -2? You gotta try, okay? So 1, 0, -5, -2. 1, -2, -2, 4, -1, 2, add them up, and you're going to be 0. So another, the polynomial we have left, this is third, so another new polynomial we have left will be what? Will be, this is double star, will be what? Will be x squared minus 2x minus 1. Excuse me. I need some water. Okay. Okay. And now we have to keep going. So we know 5 factor, we know -2 is factor. How about this? How about this one? Maybe this is can be factor too. And after you plug all the other number in and see that none of them go into this evenly, giving you 0 as remainder. It means what? It means that this is just a quadratic equation, and it doesn't give you a nice solution, probably something with radical. And we go ahead and use a quadratic formula. We see that if I go ahead and use quadratic formula, so give you 2 plus minus 2 square minus 4ac over 2a, and you see that give you 2 plus minus, this is give you 4 plus 4, give you 2, and give you 2 plus minus square root of 8, give you 2, which is 2 plus 2 square root of 2 over 2, which is 1 plus minus square root of 2. Now what happened? This is the 0. This is not the rational 0, right? But it's still 0. It's still 0. Okay. So this is still considered as 0. I mean, even though it's not rational. So if we go ahead and factor this one out, then my p of x will be what? X minus 5, x plus 2, x minus 1 plus square root of 2, and x minus 1 minus square root of 2. All of this, we have 4 factor, and 2, 0 is not rational. Well, that's what about this thing. I think I got something wrong at the beginning when I said about this theorem. It just tell you the rational 0, the interval that rational 0 is inside, right? But actually, the boundary theorem can tell you all the 0. Well, of course, it's not the complex one, you know. It's not a complex one. We're gonna go through that. Of real 0 only. Yep. Yeah, the boundary is to give you the real one. There's nothing to do with complex. But we're gonna talk about that soon. Okay, when we do the boundaries theorem, the last one. Okay, so that's all the rational 0 theorem about. But the thing is this. Because if you look at the example we had last time, you see that we also have the complex one, the complex factor. Meaning 1 over 0 can be a complex number. So what does it mean? It means the polynomial does not even have rational 0 theorem, but it could be a complex one. It could be something like this, irrational one. So how many does it have? That's the question. We need to find out how many does it have. So about like 400 years ago, I think 300 years ago, or yeah, I think 300 years ago, one of the great mathematician, German, he found out a very interesting information, and that information is the theorem called the fundamental theorem of algebra. And the fundamental theorem of algebra state that, so I'm gonna put it here. So I'm gonna put over here as the remark, the fundamental theorem of algebra. There's a whole proof in the textbook. Well, we don't have to go through the proof. And this theorem states that if the polynomial has degree of 1, if polynomial has degree of 1 or more, okay, then it has at least one complex 0. Now this is very important right here. When he mentioned the term complex 0, he means that the real one and unreal one. Because if you notice, first time you learn complex 0, a complex number, you know the complex number is the largest set. It covers the real number too. Okay. It also cover the real number and unreal one. You know. So if it's a real number, you know, it doesn't matter positive or negative, it's still considered as complex. Okay. Besides, he is also say that if polynomial has degree of n, then it has n distinct 0. It has n distinct number of 0. Well, now let's take a look at what the textbook said. This is what. Yeah. It's a complex at least one complex 0. Okay, and at most n distinct 0 at most. And did you put at most over? No, I had and at most. I forgot to put at most. distinct at most. Okay, these two information is very important, but it's pretty confusing because this, the term complex right over here. The term complex, because if it is a degree, even degree 1 or more, then it has at least one complex zero, at least one. Okay, and when it has any degree, it has at most degree, at most distinct zero. Okay, for example, if you have n degree, okay, what if you have n degree? Okay, what if the degree of polynomial of p of x, the degree is 5, then it might have 5 distinct zero at most, but at least, okay, it has one complex zero. Okay, that's what I mean. So over here we can answer that it might have at most 5 distinct zero. It doesn't matter if it's complex or not complex. Okay, they just say at most 5 distinct zero, and at least it has at least, okay, one complex one. Remember, complex over here, it means real and unreal. Okay, be careful, because sometimes some students say, okay, this polynomial has only 2, 3, and 5 as the zero, and how come it contradicts to the fundamental? Because they said at least one complex, and I don't see any complex. 2, 3, and 5 is not complex. Well, 2, 3, and 5 is actually a complex number too. Okay, so the complex number over here, it means real and unreal. Okay, so you have to be careful, because any number can be expressed as a complex number. The complex number is what? Let's just do a quick recall here. The complex number, we know the complex number is in the form a plus bi, right? Now think about any number. What if I have 2? So 2 is 2 is actually 2 plus 0. So 2 is also the complex number. Okay, so the complex number over here means real and unreal one. Okay, all right. Now in the previous video, I also mentioned in the one of the example we had a complex, the real unreal one, the one with the I as the 0. Okay, and if we say I is the 0, then negative I is also the 0 in that example. But actually, the reason we can say that, because it comes from the theorem called conjugate zero theorem. Okay, conjugate zero theorem. And the conjugate zero theorem states that if the complex number z is the 0 of p, then the conjugate of z, in other words we call that z bar, is also a 0 of p. And we did example last time already. So if 2 plus 3i is a 0 of p of x, then 2 minus 3i is also a 0 of p of x. That's what I mean. Okay. And now let me see. I can give you. Actually, well, in the previous video, I already give you the example. We try to find. We try to write a polynomial function given the 0, and in those 0, I give you a complex 0. Okay, one of them. And we already did this, but let's do another one. Okay, what if I have something like this? I have p of x equal to x to the 4 plus 2x squared minus 8. And I want to factor this completely. Okay. When I factor this completely, I mean that including 0, real and unreal, and complex, everything. Factor completely. Okay, so let's see how we do this. How we gonna factor this completely? Answer. Again, we can use rational zero theorem. We can find all the factor of this. Okay, and we plug it in this. Which one give you remainder 0? Which one give you 0 as the output? That will be the factor. There's another way that you see that this is 4, it's 2. So I can write this as if you go ahead and factor using a very traditional way we learn in intermediate algebra. So we see that this is nothing but factor of 8 will be 4 and 2, so it will be x squared plus 4 and x squared minus 2. Right? So we know right over here we have x squared plus 4, and our 2 is actually square root of 2 square, so that's a difference of square right over here. So I can write this as x squared minus square root of 2 square. Okay, so this is x squared plus 4, and this is the difference of square, so x plus square root of 2, x minus square root of 2. So you see that the rational zero theorem look like it doesn't work in this case, right? Because we have the 0 is irrational, it's not rational. So that's the reason why sometimes rational zero theorem, it just helps, you know, it does not give you everything. It does not give you all. Now if you look at the degree over here, we see that this is degree 4, so we have at most 5 distinct one. At most 5 distinct one, according to fundamental theorems in algebra. And of course I have at least, well, look like they have 2 already to satisfy the theorem. So over here they have 2 more, and you see that it's x squared plus 4. So look like if you go ahead and solve x squared plus 4, you know, x squared plus 4, and you solve for that, so you see that you have x squared equal to negative 4, then x equal to plus minus 2i. So that's why the polynomial can be written as x plus 2i, x minus 2i, x plus square root 2, and x minus square root of 2. Okay. And now how many 0? 1, 2, 3, 4, right? at most 4 distinct zero. 4 distinct zero. It didn't say 4 distinct rational zero. It did not say 4 distinct complex, real or unreal. It just say 4 n distinct zero. I mean, over here actually you can say it has n distinct complex one, because Gauss mean the complex over here mean real and unreal. But the thing that over here, you see that this is also real, right? But it's not rational. Okay, so you have to understand the fundamental theorem by Gauss carefully. Okay, so I'm gonna put over here. This is Gauss theorem. Okay, that's Gauss theorem. Alright. Alright. Let's continue what we have. So we factor this completely. Alright. Okay. Alright. So another thing, if you notice, you see that the zero could be positive or negative, could be the complex one. So on the third part of our lecture, I would like to talk about a very important rule we call the Descartes rule sign. Okay, the Descartes rule sign tell you the possible number of positive zero or negative zero, or the number of possible complex one. Alright, so what is this rule about? The rule states that excuse me. The rule states that, okay, I put the rule here. If given polynomial, okay, so the number of positive zero is equal to the number of variation inside of P of X, okay, or is less than by a whole number, or is less than by 2, by 2. I'm gonna put this like less than by 2. I think this is much better, because the textbook just say that less than by the even whole number. Actually, that is number 2. Okay, but this is confusing. If we just put the even whole number, use the even whole number, it could be 4 or 5. you know, that's crazy. So I'm not gonna put like that. So I changed a little bit so that you guys can understand better. Alright, how about the number of negative 0 is equal to the number of variation inside, okay, inside of P of minus X. Sorry, this is not P of X but P of minus X, or is less than by 2. I mean, I'm sure when you read it, it's still confusing, but I mean, when you do a couple of examples, it's not really that bad. Now let me give you the first one. Now I give you a polynomial like this. Sorry, I have pretty bad allergy. Just bear that with me, okay? 3x to the 6 plus 4x to the 5th plus 3x to the 3rd minus x minus 3. Alright, we got to check how many positive 0, how many negative 0, and how many complex one. Well, according to fundamental theorem, we have the total we have is n. Okay, the n number of 0. That's the total. So the total. Okay. So let me put the question first. Find all positive 0, positive number of 0, negative number of 0, and complex and complex 0, the number complex complex 0. Okay. Answer. Alright, we know the total is 6 according to fundamental theorem algebra. We know at most we have n distinct, so 6 distinct 1 0. Okay, some of it at most. Okay, it doesn't mean that they always have this. It's always distinct at most. Okay, but we know the total will be 6. That's the number of 0 we have, including complex and real and unreal, complex and non-complex, everything. So the total is 6. Okay, the total is 6. But how many positive? How many negative? How many complex? Okay. So you see that if you look at the P of x, how many times it changes in sign? 1. And all is less than, so just 1. Okay, less than by 2, so 1. 1 is less than by 2, so 1 is just 1. We don't have to do less than means subtraction. That's what it means. So over here, it means subtracting by 2. You know, this is only one time changing from positive to negative. So we subtract by 2, it'll give you negative. It doesn't work. So just 1 and 1. How about negative? Well, for negative, we gotta do P of negative x. We see that 3 negative 6, 4 negative 5 plus 3 negative 3 plus x minus 3, 6, 4x to the 5th, 3x third plus x minus 3. So how many times it changes? How many times? Oh, this positive, sorry. 1, right? 1, 2, right? 2, 3. 3 times. Everybody see that? Right here. 1. Okay. 2. And from here to here, 3. So they change the sign 3 times. So that's why we have 3. And subtract by 2 give you 1. Okay. But we know the total is 6. So 3 1 is 4. So we know 1 possible complex 0. And in this case, we have 5 possible 4 possible complex 0, because 1 plus, oh, this is 2, I'm sorry. 1 plus 1, 5. Well, 3 plus 1, 4 plus 2, 6. 2 plus 4, 6. Okay, so we have 1 possible positive, 3 possible negative, or 1. Or could be 2 complex or 4 complex. If it is this case, then it will be like that. If it is this case, it will be 1, 3, 2. If it is this case, it will be 1, 1, 4. Okay? That's what it is. Now let me give you another one. It's not really that bad. It's pretty easy. Okay, given x to the 5th minus 3x to the 4th plus 3x to the 3rd minus square minus 4x plus 12. Same question, okay? Answer, same question. How many possible positive, how many positive negative? We know the total is fine. Alright, so the total will be fine. And how many positive? Let's see how many times it's changing. How many times it's changing? 1, 2, 3. 3 times changing, it should be 3, right? 3 minus 2 could be 1. Oh, 4 times? Oh, no, 4 times. This one to this 2. So 4 minus 2 will be 2. Or minus 2 again. Let me do it. The total will be 5. Minus 2 again give you 0. So it could be 4 positive, or 2 positive, or we don't have any. That's what I mean. How about negative? Alright, negative. Oops. Negative. For negative, we gotta find P of negative x. Alright. Plug it in. Okay. Which is give you negative x to the 5th, negative 3x to the 4th, negative 3x, and 9x plus 4x plus 12. And let's see how many times it's changing, okay? So to go from here to here. Only one time. So we're gonna have 1, or 1, or 1. Nothing changing. Okay, only one time. And for the complex, so for the one it's gonna be 0. The total is 5, 3, so it could be 2. Could be 4. So we probably don't have any, or probably we have 2 complex or 4 complex. If we have this option, then we have 4, 1, 0. We have this option, we have 2 positive, 1 or 2 complex. And then we have this option, we have 5, we don't have any positive, and we probably have 1 negative and 4 complex. Okay, so the Descartes rule side can tell you the positive or negative. In my opinion, this kind of help you a little bit, because for the rational zero theorem, will tell you the possible number of rational only. But for the Descartes rule side, it tell you the possible number of complex one. I mean complex over here is the one with the unreal one. Okay, the unreal one. That's what I mean, the complex one in this case. Okay. So, but the complex one in the fundamental theorem algebra could be everything. You know, unreal, real. You know, irrational, rational. It could be everything. Okay, so you have to be careful with that. Okay. Now, the last one, which is I told you before. This theorem tell you the interval which contain all the real zero. Contain all the real zero only. Okay, contain all the real zero only. So this theorem we call the boundedness theorem. Okay, and again the theorem states that if given the polynomial if p of x, okay, divide, okay, divide by x minus b with syntactic division, using syntactic division, okay, and at the end it contains the last row of the syntactic division has no, which has no negative, okay, entry in the last row, okay, and remainder has no negative entry, and the remainder, it means the remainder cannot be 0. And remainder, then b is upper bound. Okay. How about the lower bound? Lower bound is if b p of x divide by x minus a, okay, x minus a, and a in this case is less than 0 and b in this case is greater than 0, okay? Okay, again using syntactic division, okay, but the last row and the last row which has alternative sign change, okay, I mean we go from positive to negative and positive to negative, and remainder then negative a, then negative a, okay, okay, then a in this case will be a negative number, then a is lower bound. I know it's kind of, you know, if you read it's kind of hard to imagine, you know, but if you do the problem, it's not really that bad. Now let me give you the example, something like this. What if I give you a polynomial function? Let's go to 4 minus 3x squared plus 2x minus 5, and we want to show that all real 0 is in the interval negative 3 and 2. Negative 3 and 2. Okay. Negative 3 and 2. Okay, answer. So how we do this? Okay. So let's do syntactic division for negative 3 for 2 first, okay? Because we do 2. Let's see, because it's upper bound. Let's check it. If this, let's check 2. So this is 1, 0, negative 3, 2, negative 5. Okay, and you drop 1 down, give you 2. Z give you 2 here. 4 give you -1. Positive 1, 2, 4, 8, 3. And you see that it's not changing sign. And the last number here, the remainder, is different from 0. So look like it satisfies this statement, right? So I can say, so 2 is up above. 2 is up above. Okay, 2 is up above. But we don't know how many in between them. It could be a lot of 0 in between, but I mean at most we have 4, but we know -3 is up above. 2 is up above. Not -3. -3 may be the lower bound. If we do the same thing, okay, 3, 2, -5. Okay, we see drop 1 out, 3 at -3, 9, 6. You see they change the sign. -18, -16, 48, and over here is 43. It's also different from 0, and it changed in the sign. So you see that we go from positive to negative, negative to positive, negative. So they changed that. That's an alternate sign change. So that's why. So -3, according to the theorem, is lower bound. Is lower bound. Okay. Okay. And because you see that, because 3, the remainder is not 0, then of course 2 and -3. Besides, we also know that 2 and we know that 2 and -3 are not 0. Because the remainder is not equal to 0. See, the remainder is different from 0, so it's not 0. So all the 0 must be in between here, between -3 and 2, and we have totally 4. So we probably have complex in there. Okay, do we have a real one? Oh, well, I don't know. We gotta go check. Okay, probably 1. 1 is the 0, probably. Okay, so you have to check. You gotta check carefully. Okay, so the boundedness theorem just tell you the interval that containing all the real 0. Contain all the real 0. Okay. Okay. But if it's complex, then of course it's not in here. You know. The complex is not in here because we're talking about a number line, the real number line. You know, the complex number is not a part of it. So just this is not a number. There's no complex in here. Okay. I mean, when I say complex, I mean the one I have R in this case. I know kind of a little bit confusing. Okay. So you for this chapter you have to read the word carefully. So this one is just the boundedness theorem. So remark. So I'm going to put a remark right here. And put a remark right here for you to remember. Now, let's see last time what color I used. Okay. So I put a remark right here. I'm going to say that the boundedness theorem, okay, give you the interval on the number line. Okay, I give you the interval which contain real 0. Okay, contain real 0. Okay, contain real 0. The real 0 could be rational or irrational. Okay, so it could be rational or irrational. But we cannot tell anything about the complex. Okay, we cannot tell. So we can. So boundedness. This theorem can tell the imaginary zero, okay, the imaginary zero, the one with the eye, okay, it cannot tell. Okay, just tell you the real one, okay? The real one, not the complex, not the complex, not the imaginary. Let me use that term, because if I use complex, then maybe someone is really confused between complex cover real, unreal, rational, irrational. So it cannot tell anything about imaginary zero, because this is a bit of interval notation. Think about it, it's on the number line, and if it's imaginary zero, which is I, containing I, right? You cannot put I on the number line. It doesn't mean anything. Okay, good. So I'm gonna stop the lecture over here. I know that this video one of the hardest concepts in pre-calculus. So I want you to learn this carefully. Okay, if you have any question, please just let me know. I'm willing to reply any question. Just send me the message. And the homework, I think the homework will be easier. But try to understand each example over here carefully. Okay. Then if you don't get it, just send me a message. Okay. I will reply really fast. Okay. I'll be seeing you next time for the new lecture. Bye bye.